Have you ever wondered how people turn a general purpose AI model into a coding assistant, a medical chatbot, or a legal assistant? It might seem like they retrained the entire model from scratch, but in reality, that's rarely what happens. Instead, they use a technique called LoRA, short for LoRA adaptation. LoRA has become the standard method for fine-tuning modern large language models like Llama, Quen, Gemma, Mistral, and DeepSeek because it dramatically reduces the amount of computation and memory required. In this video, you will learn what LoRa is, why it works, and most importantly, the mathematics behind it. By the end, you understand what exactly LoRa is and why it's so efficient. Let's begin with the problem. Modern large language models contain billions of parameters. These parameters store everything the model has learned, from grammar and reasoning to programming, mathematics, and word knowledge. Suppose you want to teach the model something new. Maybe you want it to answer customer support questions, maybe you want to summarize research papers, or perhaps you want it to specialize in medical diagnosis. The traditional approach is called full fine-tuning. During training, every parameter in the model is updated. If your model has 7 billion parameters, then all 7 billion parameters must store gradients and be optimized. This requires enormous GPU memory and a significant amount of computation. Researchers then ask a simple question: do we really need to update every parameter just to teach the model a new task? The answer turned out to be no. LoRa approaches this problem differently. Instead of changing the original model, it freezes every parameter inside it. The pre-trained model keeps all the knowledge it has already learned. Then LoRa inserts more trainable matrices into selected layers of the transformer. Only these new matrices are updated during training. Think of hiring an experienced software engineer. You don't simply erase everything they have learned before giving them a new job. You simply teach them the skills needed for their new role. That's exactly how LoRa works. The original model stays untouched. Only a very small number of additional parameters are trained. Now, let us understand the mathematics. Suppose one of the weight matrix inside our transformer has dimension 1000 by 1000. That means it contains 1000 multiplied by 1000, which is equals to 1 million parameters. If we perform full fine-tuning, all 1 million parameters must be updated during training. Now, here's LoRa's key idea. Instead of learning a completely new weight matrices, we only learn a small update. Mathematically, we write our updated weight matrix W prime is equals to original weight matrix W plus delta W, where delta W represents the change or updates that we want the model to learn. So instead of modifying W directly, we only learn delta W, but LoRa goes one step further. Instead of learning delta W directly, LoRa learns two smaller matrices. We write delta W equals to B multiplied by A, where matrix B has dimension 1000 by 8 and matrix A has dimension 8 by 1000. When we multiply these matrices together, it produces 1000 by 1000, which matches the original size of the weight matrix. So mathematically, W prime equals to W plus B multiplied by A. Now, let's compare how many parameters we are training. With full fine-tuning, our weight matrix contains 1000 by 1000, which equals to 1 million trainable parameters. Matrix A contains 8 by 1000, which is equals to 8000 parameters. Matrix B contains 1000 by 8, which is equals to 8000 parameters. Together, 8000 plus 8000 equals to 16,000 trainable parameters. Think about that for a moment. Instead of training 1 million parameters, we are only training 16,000. That's more than 62 times fewer parameters. Yet, after multiplying the two matrices together, we still obtain a full-size update matrix. This is the genius behind LoRa. Rather than learning a huge update directly, it assumes that the updates can be represented using two smaller matrices. At this point, you might be wondering, if we are updating so few parameters, why doesn't the model lose performance? The answer is that the base model already contains an enormous amount of knowledge. It already understands language, reasoning, coding, and general concepts. Most downstream stacks don't require rewriting everything that the model knows. They only require making small adjustments to how that knowledge is used. LoRa captures those adjustments efficiently using LoRa matrices. That's why it often achieves performance very close to full fine-tuning while using only a tiny fraction of the trainable parameters. LoRa offers several important advantages. First, it requires much less GPU memory because only the adapter matrices store gradients. Second, training is much faster since far fewer parameters are updated. Third, the adapter files are tiny compared to the original model. Instead of saving another 7 GB model, you may only save a LoRa adapter that is a few hundred megabytes. Finally, LoRa is modular. You can keep one base model and load different adapters for coding, customer support, translation, summarization, or any other tasks. One model can perform many specialized tasks simply by swapping adapters. So next time someone tells you that LoRa fine-tunes only a small number of parameters, you know exactly what they mean. Instead of updating an entire 1 million parameter weight matrix, LoRa freezes the original weights and learns two much smaller matrices. One with dimension 1000 by 8 and another with dimension 8 by 1000. Together, they reconstruct the update matrix while requiring only 16,000 trainable parameters instead of 1 million trainable parameters. That's the mathematical insight that makes LoRa one of the most important breakthroughs in parameter efficient fine-tuning. Thanks for watching. I'll see you in the next video.